I'm very pleased to introduce Eric Chung. I've known Eric for 6 or 7 years when we worked together on the RAMP project. There was quite a number of people on that project, and he was one of the very few that made any sense. He's finally finished his degree at CMU and has done a year and a half at Microsoft as a postdoc, and now he's interviewing for a position here, and welcome.
All right, thank you, Mark. So I'm absolutely delighted to be here today. Today I'm going to talk about a couple of projects, 2 projects, in which what we're trying to do is address this growing need for hardware-based specialization. And what I'm hoping to persuade you is that we can make hardware easier by raising the level of abstraction. So this is work that began when I was a grad student at Carnegie Mellon and it's carried over to new directions at Microsoft Research, and we're based out of Silicon Valley. So I first want to acknowledge many individuals with whom I've collaborated with, and those who've also been amazing mentors to me over the years. And you can see who they are and what projects that I've, and Mark actually mentioned the RAMP project, so Mark, you're on there too. So we are in the midst of a significant disruption. So you might have heard it called different things. Some people call it end of Dennard scaling. Some people have called it the era of dark silicon. I really like to see of it as an era of opportunity for architects. So there's the good news and the bad news. The good news, if you look at ITRS, is that we continue to expect exponential increases in transistor density. So if you look at the scaling trends, by the end of a 10-year scaling roadmap, we're going to have 16-fold transistor density. So it means the transistor is going to get 16 times smaller. You might have also heard the bad news, which is that supply voltages have not been scaling commensurately. And a lot of that has to do with our ability to control threshold voltage and variability. So supply voltages aren't changing a whole lot, and what that's leading to is an incommensurate mismatch between the transistor and the power it dissipates. What that means is if the transistor is 16 times smaller, it's only dissipating 4 times less energy. Right? So that's a significant problem. Right? So it was forecasted 6, 7 years ago that we'd have hundreds, if not thousands, of cores. If you look at what's available now, we're in the regime of 4 to 8 general-purpose processors. So the key here, however, is that in order to make up for this deficit, as architects, we have to be able to do more with less, right? So we effectively have to get better performance for less energy per second, power. And the ramifications of this are widespread. It affects all things big and little. If we look at, in a data center, I put these things next to power stations. I'm only going to be able to deliver tens of megawatts of power in order to power the devices as well as cooling them. And we're already facing a lot of limitations in being able to increase the computational density of our data centers. The problem is even more acute for energy-constrained devices. Right? So not only do we have this end of Dennard scaling, we have 3-watt battery-limited devices. You've got a 2,000 milliamp hour battery, and you've got to work with that. Right? In 2010, we carried out a study in which we were exploring the trade-offs between general-purpose architectures and more specialized architectures. So we looked at architectures like off-the-shelf multi-cores, embedded processors, state-of-the-art GPUs, FPGAs, and even at custom logic. I'm not going to go into too much detail, but needless to say, relative to the general-purpose processor, anything else gets you improved energy efficiency. So those are the numbers that I'm showing. Those numbers are kind of approximate, but generally the ballpark order of magnitude. So for embedded cores, you get about 2 to 4x improvement. FPGAs and GPUs get you 10x. Custom logic gets you about 2 orders of magnitude. So these are ASICs. So back then, this was all prediction. If you actually look at what's coming out on the market now, embedded-like processors, so ARM chips, are starting to infiltrate the data center. So companies like Calxeda and numerous other startups are starting to develop embedded-like cores for data centers, this here is my favorite chip called the Zinc Chip. This is a chip manufactured by Xilinx in which it's FPGA and ARM cores on a single die. And actually, I think it represents a pretty significant milestone in heterogeneous computing with FPGAs. This chip I'm showing you next is the IBM WireSpeed processor. This came out about a year or two ago. And you can see in the picture that you have PowerPC cores in the die photo up here. And down here, you actually have dedicated cores for functions like regular expression matching and XML. And GPUs, of course, are the poster child for heterogeneous computing acceleration. So I won't say much further on that. So hooray. Specialized hardware is here. We're done, right? Not yet. So though the hardware is here, there isn't really much of a compelling story for software. Okay, so programmability and abstractions are serious issues. And I see a lot of interesting parallels to what happened 6 to 7 years ago when we made the transition from uniprocessors to multiprocessors, where we suddenly realized, okay, how the heck do we program these things? Okay. So my goal is to, in a sense, make specialized logic accessible to the masses. Okay, how do we put these capabilities into everybody's smartphone? How do we put these capabilities into the data centers? And how do we provide abstractions to program them? So I think there's a lot of work that's been going on in the multi-core GPU space. Two leading contenders right now for specialized hardware, ASICs and FPGAs. So ASICs, as I said, of course, have raw potential, but they completely lack flexibility. Another problem with ASICs is that due to the time it takes to design, validate the masks, fabricate, it's several years before you actually see your feature implemented and deployed. So what that means is that you have to know several years ahead of time what function you want for the specific market that you're trying to sell your chips in. And a way to reconcile that is by using an FPGA. So an FPGA is a field programmable gate array. And the idea is that it's a sea of reconfigurable logic that can be repurposed to any logic function subject to your capacity. And it's not as efficient as the ASIC, but for certain classes of applications, you can get significantly better efficiency than conventional systems. Of course, FPGAs have a lot of raw potential, but today it still takes hero Verilog designers to program them efficiently. Okay, so currently, although the hardware is here, there's just no sustainable way to get people to use these systems. So Andre Dehaan, I plastered his name in a lot of places with this quote. So he probably doesn't appreciate that I associated him with this quote. But so FPGAs are really not architected in mind to be computing devices, right? So currently, commercial FPGAs are meant to compete with ASICs. And so what that means is that they expose a very low-level abstraction that's very similar to like designing an ASIC. And that permeates everything from the architecture layer to the tools. So I'm going to talk a little bit about FPGAs and some work we did at CMU in which we're trying to raise the level of abstraction of how we program FPGAs. I'm going to start with a little bit of anatomy. And I'm sure most of you don't need this, but just to bring everyone to the same page, the FPGA is essentially a sea of reconfigurable logic. The basic building block is what's called the programmable lookup table. The lookup table that I'm showing on the right is a tiny little SRAM, typically on the order of 64 entries and 1 bit wide, and allows you to essentially configure a 6-input truth table. You have these lookup tables, and you can compose them through switch boxes and interconnect components in order to form more complicated circuits, and there are state elements. There's another component on the FPGA that's very important. It's called the block RAM. So the FPGA is made up of hundreds, if not thousands, of tiny distributed SRAMs, and that in aggregate provide you terabytes per second of memory bandwidth. And that's one of the key reasons why FPGAs are able to do so well in terms of raw performance and capabilities. So the SRAMs typically are used as a staging ground for applications. So very often for any application or kernel you're mapping to the FPGA, you use the SRAMs to basically stage the inputs. You compute out of the block RAMs, and then you write the outputs out the same way. Now, FPGAs can be used in a lot of different settings. They could be used in a network card. Let me kind of constrain the space here. So we're really looking at FPGA as a vehicle for computation as a coprocessor to augment general purpose systems. Okay, so we're not talking about anything else. So these are two potential ways you can organize the FPGA. At the top, you have a shared memory multiprocessor where the FPGA is connected on the memory interconnect. And there are socket-based accelerators you can buy off the market today that do this. Kind of more tightly integrated design here is a single chip multi-core where the FPGA fabric is connected on a network on chip and also is coherent with the caches on die. So this is kind of like my tongue-in-cheek description of what it's like to program an FPGA. So this is my entry point into programming a commodity off-the-shelf FPGA. So I have the sea of gates, and I have my application. Okay, so how I get to the application really doesn't matter. So you can employ high-level synthesis tools. You could design it by hand. You can use library IP code, IP cores. But how I get here actually is not important. There's also the requisite SRAMs that you attach to the application. Okay, so as I said, the SRAMs are a staging ground for bringing in data. Now, one of the most difficult things with using FPGAs is how you handle communication and data management. Okay, so how do I actually bring data to? How do I bring the operands from off-chip memory to my application? So if you think about it, in a general purpose processor, when I'm programming it, I have loads and stores as kind of a basic primitive that's available to me in the instruction set. I issue a load, and the data essentially is fetched by some cache controller. Essentially, there's an entire automatic, it's all automated away from me. I don't see how that data gets there. On the FPGA, that's not the case. On the FPGA, the notion of communication, memory hierarchy is all treated as a user kind of problem, user responsibility. And you have to do this each and every time you go from platform to platform or from device to device. So the key here is that we don't really have any clear boundaries or abstractions between what should be the application and the rest of the system, the microarchitecture in a sense. So just to give you a concrete feel, as a designer, you often meddle with things like memory controllers, okay? Not only that, for each application, you often end up developing an application-specific network on chip, and you have to customize this for each and every application. Last but not least, you have to deal with vendor-specific control logic. So in each of the 3 or 4 FPGA platforms that I've used over the years, each of them export a different type of interface and protocol. And every application has to be ported to each of these types of systems. Okay. Now, this picture isn't doing things justice because this isn't just 7-ish SRAMs. We're talking about hundreds, if not thousands, of endpoints on big FPGAs. Right? And the control logic's distributed. The network on chip is non-trivial as well. And as I mentioned, there's no portability. So this is going back to what I said. If I look at off-the-shelf solutions, different FPGAs platforms expose different capabilities. Once my platform changes, my application becomes obsolete. So this is work that we started around 2010 at Carnegie Mellon, in which the purpose of this was to build a standardized memory abstraction for the FPGA, really just a general way of managing communication that unifies how we place data on chip and how we move data from off chip to on chip. So the key idea is that we don't want people to meddle with memory controllers, so that's all abstracted away. And there's also a notion of a global address space, as you would in a general purpose processor. Rather than forcing you to develop an application-specific network on chip, we're going to give you something that's general purpose and actually baked into the FPGA fabric. The reason why we want to do this is because, number one, it doesn't cost us very much if we actually implement the network on chip as an ASIC on top of the FPGA. Okay? Not only that, it's going to beat any application-specific design I do because it's operating at a clock rate that's much faster than if I were to implement it natively on the FPGA. The last but not least is kind of a leap here, which is rather than having the user orchestrate the data movement using a low-level RTL-like abstraction, we're going to replace it with software control threads. Okay. So the key idea here is that, so I've subtly replaced the word SRAM with CoRAM. CoRAM should be thought of as a software programmable scratch pad. And that's not a new idea, but think of many distributed scratch pads on the FPGA In order for the user to access any kind of data on and off chip, they have to go through the CoRAMs. So that's a standardized boundary between the user application and the rest of the system. The user also specifies these control threads that orchestrate the movement of data. So I'm going to dive into kind of several concrete examples. And when I mean, this is hello world on the FPGA, I really mean that, hello world. That you only have to write this amount of code to actually get a complete system running using our tool chain, which I'll talk about a little bit later. So this is kind of the simplest application you can imagine. You have your pipeline or core logic. You have a single module called the CoRAM, and this thing called the channel FIFO, which I'll get to in a minute. So from the end user's perspective, they treat these modules as black box components. So they don't get to look inside how they're implemented. But within the context of their application, when I need an entry point to memory or I/O, I instantiate these CoRAMs on demand. So what does a control thread look like? The control thread looks a lot like software, but don't be fooled. It's more of a stylized way of expressing a state machine. So the first thing I'm going to show you are static functions. So these are accessor functions that have to have static arguments. And these are essentially typed objects that refer to objects I've instantiated within my RTL. Okay? And what's important about this is that once I have handles to these objects, I can perform operations on them. So this looks a lot more declarative, right? In the sense that I'm just expressing my intent, but not having to express how the work is carried out. So the write RAM operation takes as argument the CoRAM object, C0 here. The second argument is the SRAM address, where I want the data to end up in the CoRAM. Global address, think of it as a global value in memory, and the size of the transfer. So this is a lot like a DMA operation. And last thing, so after this operation completes, the thread also needs to inform the core logic that, okay, the data is ready to be consumed. Go ahead and work. So that's what the channel FIFO is for. It allows the threads and the core logic to communicate. This is kind of a toy example, so let me get into something just a little bit more non-trivial. This is how we do matrix multiply. So this is square matrix multiply. You take two input square matrices and produce one output square matrix. The way we've organized this, so the stuff on the left is all the core logic. You have a parallel array of processing elements. So think of these as specialized cores for computing dot products. Okay? Inside each of these processing elements, you have these input CoRAMs. Okay? So think of these as scratch pads the user instantiated, and a single output CoRAM. And in the center here, you have essentially a multiply accumulate engine for performing dot products. Okay? There's also these channel FIFOs, which will become clear in a moment, which are used for synchronization. So this is what the control thread looks like. The control thread in the body of it doesn't have anything that's compute related. It's really, think of it as a thread almost for prefetching data. So here, I can actually do things like address calculation. So I have the triple nested loop that you expect in a tiled matrix multiply implementation. You have the first operation, which is a read channel. And think of this as a blocking operation. So all the state machines have to issue a token, which until the control thread receives all of them will block. After it receives the tokens, it unblocks and now begins initiating sequences of memory transfers. Okay. Now this write RAM is actually taking an argument that I'm not showing in detail, the input RAM top. So in this abstraction, the input RAM data type can be used to represent a collection of memories as well, or memories of different types of aspect ratios. And when we perform operations on them, we respect those kind of configurations. There's, of course, address calculation, the writing into individual RAMs, the global address. I'm not showing you the details of, I'm only showing you for the A matrix. There's also B matrix and also a write back operation for the C matrix. Now, if you're paying close attention, you'll notice that this is not a good implementation of matrix multiply because I'm serializing. So in the control thread, I have one I'm basically waiting until all the data is present before I actually inform the processing elements so you can start computing. So we have a variant of this where you can actually issue operations in a non-blocking fashion. So if you want to be able to parallelize computation and memory transfers, you can do that as well. Okay? And that's important for performance. So the control thread really should be thought of as kind of a wrapper around your core logic. And it's really meant to be a high-level description of your application's memory access pattern that, that which some system has to target to an actual implementation. So this is my last example, which is stream FIFO. So streaming is actually a very common pattern in FPGA-based applications. So what we do here is we take a CoRAM, we instantiate it, and we use it as a circular buffer. And the idea in a circular buffer is you have a producer and a consumer. The consumer, in this example, is going to be the logic that's sitting off to the left off the screen. The producer, nominally, would be some DMA engine that the user would build with a network on chip to the memory controllers. But in this example, in CoRAM, the producer is actually a control thread that's really just specifying the movement of data. And what happens here is that there's fine-grained communication between the stream FIFO component and the control thread, such that the control thread is aware of how much occupancy is in the CoRAM. Okay, and I won't go into those details. But the critical thing here is that we can use CoRAM and control threads to compose portable, reusable memory, what I call memory personalities, that we can create interfaces and abstractions that are best suited for specific different applications. And so I've shown you streaming, Scratchpad. In the papers, we've also looked at things like non-blocking caches. So there are a lot of different things you can do with these memory personalities. So this is kind of the 10,000-foot view of how we envision CoRAM being implemented. What kind of substrate would be best matched to this abstraction? And the way to think of it is that CoRAM at the top level, what the user level sees is architecture. And the dotted line below that is microarchitecture, right? So any implementer could decide whatever they want to do at the bottom. So what I'm showing you here is, at the bottom, what I call this compute-centric FPGA. This is an FPGA that doesn't exist, where rather than just a pure sea of gates, I have mechanisms to support the abstractions very efficiently. So at the bottom layer, I might have dedicated memory controllers. I might have TLBs if I want virtual memory. I have a dedicated network on chip. And I also have these tiled units that are replicated, where there's fabric, which is, that's the term for the FPGA fabric. These green boxes are the CoRAMs. And we also have specialized DMA engines that are used for tracking the transactions and be able to handle request responses. And there's also this box here, which is control threads. So it all sounds very high level. The question is, how does this high-level abstraction get mapped into an implementation? So what we did is we developed what's called a core flow compiler. So this is an end-to-end tool that takes your portable application and maps it into implementations on existing FPGAs. So we can, in essence, emulate CoRAM on FPGAs that we already have. We've also done some studies on, looking at future FPGAs with these mechanisms. So at the heart of the tool flow, essentially what we're doing is rewriting your application. So you start with your RTL, and in a sense, we're synthesizing a memory system and linking it in with your application. And you can link in different platform specifications, and that's how we get portability. And the nice thing, of course, is also the user essentially doesn't have to deal with all the mechanisms. We also give the user the notion of constraints. So the idea here is that, okay, it seems like it's high level. How do I control the implementation? So we have these kind of soft constraints where we can say, well, actually, a network of this topology makes a lot of sense for our application, but shouldn't affect functional correctness. Then, of course, we can target, we essentially generate RTL and target standard commercial EDA tools. We can target simulators and FPGAs. And so I didn't talk a lot about how control threads are implemented, but the control threads shouldn't be thought of as general purpose C. It's really a way of expressing a state machine. So you can't do things like memory allocation or recursion. So one way we happen to implement is simply synthesize state machines directly from it. So we use the LLVM compiler, essentially take the high-level descriptions and synthesize an FSM. Another way you might do this is to have dedicated microcontrollers. So many ways to get there. But our specification doesn't demand a specific way of implementing things. The other problem, of course, is data distribution. How do we route operands efficiently? The problem we're faced with is that there are potentially hundreds, if not thousands, of endpoints distributed on my chip. I have multiple, if not tens of memory ports that I have to access. And I potentially have to support up to hundreds of gigabytes per second of memory bandwidth. Okay, so I have to be able to provide end-to-end connectivity. The naive way to do it is essentially turn every one of these CoRAMs into a router or a client on the network. Of course, that quickly runs into scalability issues, so we apply the technique of aggregation. So what we're doing is essentially consolidating groups of RAMs together into so-called cluster DMAs, and these are essentially endpoints on the network on chip. Of course, you have to be intelligent about how you map your CoRAMs now, because if I have multiple CoRAMs that are, in a sense, memory intensive, I'm essentially pushing a lot of traffic through them, I want to map them in a distributed fashion across these endpoints, because the cluster essentially has a fixed allocation of bandwidth to the network. So this is some evaluation we carried out, and what we're doing is comparing 3 types of FPGAs. Okay, so the first FPGA is what I call the ideal FPGA. So think of an FPGA where the only cost I have to pay is the core logic, just my application. So if I have memory controllers or network on chip, I don't have to pay that cost, and I have instantaneous links to off-chip DRAM. Okay, so this is kind of a configuration that tells us, this cannot exceed this level of performance or efficiency. The next design point is the soft CoRAM, where essentially we're using the core flow tool that I discussed and targeting a conventional FPGAs using soft clusters and soft network on chips. And there we actually experiment with different types of topologies. The last configuration is what I call hard CoRAM. So if we take an FPGA and actually introduce these mechanisms that I talked about, what would we get? And one thing to note is that the CoRAM clock, which is the clock rate at which the network on chip operates, is considerably faster than the soft logic, right? And that's because I've actually deployed it as an ASIC. And of course, we're looking at different configurations across technology generations and also commensurately increasing memory bandwidth. We look at a variety of different applications that range from dense regular to sparse irregular. I'm only going to show one result today, which is the MatrixMultiply, but the rest of the examples follow similar trends. And of course, everything is based on synthesizable RTL. So this is the first graph I'm going to show. Each of these major categories are different FPGAs of varying capacity. So this is an FPGA with 4 million gates. Within each category, we're looking at 3 configurations. We have 3 soft CoRAM versions, soft networks. We have the hard CoRAM. We have the ideal. So if you look at the black bars here, this is essentially cannot exceed performance. Okay. The next set of bars I'm going to show is if I have hard CoRAM, and not too surprisingly, we're able to match the ideal performance. What I'm going to show you now are the green bars, which is what the soft logic, how the soft logic implementations do. You can see for small scale configurations, the soft logic implementations actually do reasonably well, with the exception of the ring network. So you expect, as you get to larger configuration, the bisection bandwidth kills you, so you just can't do anything with it. But we get up to even 1,000 cores, and actually the soft crossbar does pretty good. So you might ask is, does it actually make sense to do hard CoRAM? Well, the thing I'm not showing you is area. Okay, how much did it cost me to actually implement these mechanisms? So what I'm showing you now are exactly the same categories, but now a different set of bars. The core logic is shown in blue, which is the stuff that's the matrix multiply kernel, and that essentially is not changing, right? Except when I go from increasing FPGA generations. The stuff that's in red is the cluster DMA stuff I talked about, and these are essentially little engines that are used for giving you memory level parallelism. There's also the network. Right? You can see that, as you'd expect, when you get to large configurations, the soft crossbar just runs into serious scalability issues. The ring's cheap, but it doesn't perform well. And if I overlay efficiency on top of that, which is performance normalized to area, you can see that there's still a significant gap between soft implementations and the ideal and the hard. So the hard implementation does pretty well, close to ideal, and the soft implementations are roughly about 2x worse. And we see the same trends in the other applications as well. So that's that. So another thing I want to mention is that the hard implementation, I didn't show you the area, but it's on the order of a couple percentage in terms of die area. So you don't pay very much to actually have these mechanisms while preserving this abstraction that I told you about. And we have a lot more applications in detail in the paper. let me kind of tell you about some of the recent work that's been happening. We're actually doing a little bit of prototyping. So this work is mostly being a CMU-led effort, but essentially the RTL that's being generated by my framework, we're fabricating a test chip in order to get very credible energy numbers. So this here is a 130 nanometer die stack, where what we're doing is on one layer, you have the FPGA and the application, and on the second layer, you have the overlay network on chip and also the cluster DMAs. And of course, you have interlayer links using TSVs. And roughly, we're expecting tape out at the end of this month. There's another recent work that we've done, which is trying to make CoRAM more practical on conventional FPGAs. One of the reasons why we're seeing such a big area overhead is because we're relying on a general purpose network on chip, right? So we're deploying a mesh or a ring or a crossbar. It turns out that a lot of the connections can be pruned, right? So if you're willing to put in the effort, you can basically say, well, these two endpoints don't actually communicate. We can prune those edges. And at the same time, traffic isn't asymmetric either. Very often, I might be reading more data than I'm actually writing. So I can scale my networks in an asymmetric manner. So I'm more happy to talk about those, this newer work offline. So we've also tried to do a lot of outreach. So this is CoRAM for the masses. So we've done a lot of tutorials. We've released the infrastructure in the form of a web interface, so people can actually go on there, try out CoRAM as an abstraction, and generate a design that will work out of the box for a variety of platforms. This is just a picture of the CoRAM in the browser. There's a YouTube video with a tutorial of myself in the corner there. You can also select different applications and basically click a button. It'll email you the design files. You hit go, and it'll run on the platforms we support. And one of the cool things is that we can actually target both Xilinx and Altera FPGAs, which to my knowledge isn't possible today using standard tools. Okay. So before I get on to the sort of next phase of this talk, let me pause for a second. Does anyone have questions?
So what do you think are the most promising applications for this style of computing? So let's say you could get these tools out there, have every PC have this hardware. What would be the most useful applications?
So one of the things is, this is big data applications. So one of the things CoRAM is really good is managing data. So especially if I have computations that don't fit on chip, it's just a very natural way for me to implement tiling or partitioning. And actually, if you wait till the later part of the talk, I'll actually talk about a specific application we did at Microsoft that actually composes very well with CoRAM. Any other questions? Oh, by the way, I think I'm supposed to state what the question was. So the question was, are there any good applications that match well with this? OK, so I'll move on. So I want to talk a little bit about my broader agenda. So CoRAM really attacks the problem from the bottom up. Right? So CoRAM is trying to raise the level of abstraction of hardware, but there's still a very huge gulf that we have to traverse. Right? So special purpose hardware is a very disruptive thing. And one thing I've been looking at is really how do we gracefully integrate special purpose hardware into rich software ecosystems, right? If you look at what's actually running on smartphones today, people use high-level programming languages. They have software, compiler runtimes, a lot of libraries. And hardware is this thing that kind of sticks out in a funny way. We're very used to having this instruction set boundary that kind of separates things, right? And also, the way people kind of traditionally have done things is, I'm being cynical here, is that people who work in this area, we take the application, we throw grad students at the problem. So this is the hero Verilog approach. We get a design that maps efficiently on the FPGA, and then we publish a really nice paper, right? But the problem is there's no sustainable methodology, right? There's no sustainable methodology to build an ecosystem. There's no software stack, in a sense, for special purpose hardware and FPGAs and even ASICs. So what I kind of envision is that coming from the bottom up, you have this portable hardware abstraction layer. And hopefully convince you at this point that CoRAM is an example of this. Coming from the top to the bottom, the question is coming up with interesting interfaces between hardware and software. And this is where I think things get really murky. So we tend to think of hardware as this very rigid entity. It's an IP block that someone thought up of, and it comes out to market several years. There's no notion of agility. If I want to adapt my application to do something different, I don't have that capability. So one area that I'm really interested in is exploring this notion of malleable computational templates. The idea behind the template is that it's sort of like an IP block that's highly parameterized, but a lot of its functions are not defined until the compiler or the runtime decides so, right? So to give you kind of a concrete example, if you look at substring matching, you look at dynamic time warping or sequence alignment, they all have three things in common, which is dynamic programming. And the way you typically implement dynamic programming in hardware is using a systolic array. So in the systolic array, essentially you're mapping the table into hardware, and you have kind of this orchestrated nearest neighbor communication where cell updates are kind of propagating in a diagonal wavefront. So, however, you look at these three different applications, people have published works in different venues having built this thing without realizing that the systolic array is the same thing. They've all done the same thing. The only thing different is that the data types are different and the cell update functions are different. So that's what I mean by, we should build a template like that, where at runtime, the runtime can essentially configure what the data types are, configure what the update functions are, but at the same time, we've leveraged designer knowledge. The designer knows how to build a very efficient systolic array, and so that's how we can, in a sense, reconcile efficiency and productivity. So I'm going to give a concrete example of a computational template. This is work that we've done at Microsoft. So this is work called LINQits, which we call big data on little clients. There's also some other work we've done on sparse matrix acceleration, which I won't have time to talk about today. So LINQits is really what I call a computational template for accelerating big data. Okay, the application domain is really query processing. Okay, LINQ is a lot like SQL or relational databases, the database operators, with the difference that there's a way of specifying higher order functions. So I can, in a sense, use basic operators like selects, wheres, and joins, but I can parameterize their behavior using arbitrary C# code. So we think LINQ actually happens to be a very natural boundary between hardware and software, and also a very good candidate for acceleration. The reason is because LINQ has been used, for instance, to do things like data mining, k-means clustering, Black-Scholes. People have used to do linear algebra. LINQ has also been used for parallelizing the body tracking pipeline and the Connect sensor that came out of Microsoft. So there's been a lot of success stories in using this effectively a domain-specific language to do acceleration. So what we were trying to do is essentially take LINQ, and the other thing that's important is that it's declarative. It doesn't say anything about how I should be implementing these queries. So this is an example of a select query where imagine, so queries are operating on collections of data, and here I'm taking each element of that collection and essentially taking its sub-element and creating a new collection. So that's the simplest example. So we want to deploy this in a lot of different settings. One, in the data center. So we have coprocessors in the data center, and these are actually things that are coming out onto market now. IBM, for instance, is selling these kind of systems. You can imagine being able to do this in the cloud, and if you have LINQ queries in your applications, you can exploit them. In the mobile system on chip, energy-constrained mobile devices, one way you could think of is actually pushing big data to the clients. So you can, now that you can sort of drastically improve the capabilities of devices, you can imagine more functions actually running on the client and making them more self-reliant. There's also emerging classes of stacked memory. So this is a Micron hybrid memory cube. You have essentially TSVs going through, and there's a logic layer at the bottom, and a lot of open questions are what do you put in that logic layer? Right. So this is the target system that we're playing with. It's called the Zinc Chip. As I said, Zinc, I think, is a pretty significant milestone. It just came out last year. This is a chip that's sold by Xilinx. You can buy an eval board for about $300. And on the chip, you have two out-of-order processors. These are dual A9 cores. And you have FPGA fabric. It's all on a single die, and they communicate through a coherent interface. And it's a whole system on chip, so you have memory controllers and I/O devices, Ethernet. And what's cool about this, it runs standalone software, and there's actually a growing software ecosystem around it. So that's very exciting. Most importantly is that the Zinc, we've actually measured this, runs in the power envelope of about 2 watts. So to us, this is actually a chip that is a proxy for prototyping a hypothetical mobile device, a system on chip that might have some reconfigurability in it, and we can get some credible power numbers. So this is kind of how we envision the high-level software to hardware flow. So the high-level application has C#, and a subset of it is in LINQ. And there's a query plan that takes the query and generates essentially a DAG. So these are different operators like selects, group bys, and joins. And there's also these higher order user-defined functions that I talked about. And what it's doing is essentially configuring what I call the computational hardware template. It's a highly parameterized hardware block that you can configure at compile time, and you can also configure its behaviors at runtime. So we can, at compile time, select multiple operators to be included, and then at runtime, we can select which operators to actually run. What I'm showing you here on the left is a C# runtime that's modified. So this is kind of how we envision things. We haven't actually built this in the software runtime yet. But the way we envision is that the runtime would essentially run the parts that's not LINQ on the ARM A9 cores, and then, of course, the hardware run as LINQits on the system on chip. I should also explain LINQits comes from link plus circuits together. Another thing I want to mention is that one hypothetical deployment scenario is actually compilation in the cloud. So if we're able to embed, if you think of, there's a growing trend of verticalization in the industry, right? So vertical ecosystems. You look at major companies like Apple, Oracle, Microsoft, actually, things like Android devices. There's this kind of walled-off garden where all applications are basically managed and deployed. This is a place where you can apply things like post-compilation optimization. So the application's already there. We're able to preserve some of the link information, and without the user intervention, we can apply these optimizations. So the user programs in link, and they don't know that there's an FPGA going on. They just see things go faster and more energy efficient. And that actually also creates a virtuous cycle where, OK, I see that happening. I'm going to try to cast more of my computations using this abstraction. So I'm going to go into just a quick detail about some of these link operators. So GroupBy is something that's very popular and used in a lot of different applications. So I'm just showing you a little bit of code up here. Everything that link applies to is in terms of collections. So there's a type called IEnumerable. So source here is a collection of data, 10 integers. And best is basically saying source, apply the GroupBy operation. And this is here is a user-defined anonymous function that takes each element and maps it into a key, where the key is essentially the element mod 4. Okay? So when I actually compute, in what's blue here, these are the keys. Okay? So I've shown this in order, but it doesn't actually have to be in order. So what GroupBy is doing is basically taking each of the key value pairs and sorting them into buckets according to a common key value. Okay? So that's it for GroupBy. GroupBy actually turns out to be a pretty challenging thing to implement because you don't know ahead of time how many groups you need, right, and the sizes of the groups. Okay, so it presents an interesting challenge in terms of optimizing for your memory hierarchy. So this is just, I'm not going to expect anyone to read through this, but this is an example of doing k-means clustering using LINQ and GroupBy. Okay, so this is the query. It fits on just a couple of lines in the user-defined function. I have 3 different operators, GroupBy, select, and aggregate. And this is how I actually carry out the query. Okay, so you can see it's a very succinct way of expressing a code. So to implement GroupBy in hardware, this is what I'm going to show is kind of a naive implementation. Okay, so the idea here is that we're working with very large data sets. So data sets that won't easily fit into on-chip memory. In hardware, we're going to have synthesized user-defined functions. And how I get here can depend on a number of ways. One is by using conventional high-level synthesis tools to synthesize the user-defined functions, or you could imagine microcoded engines that can actually execute it as code. The network on chip here is essentially is a component that performs fine-grained steering of the key value pairs. So values come in here, generates key values, goes into the network, and this is kind of a naive implementation where we're essentially implementing an on-chip hash table. Okay, so you think of GroupBy, I'm just going to take the key, index a hash table, and then keep appending to that entry. The obvious problem with this approach is that the on-chip hash table isn't very big. On an FPGA, at most, I have several megabytes of capacity. So at the moment, I have many more keys than I have entries in my hash table, I'm hosted. Okay, and so that's not a very compelling case with using the FPGA. So we're actually leveraged this pretty well-known idea, which is hash partitioning. So the idea is to take a divide and conquer approach to solving GroupBy. And what we're giving up is we can't do this problem in a single pass. what we're going to do is actually reprocess the data multiple times. So in the first phase, rather than trying to group everything at once, we're going to split it up to 2 groups, for instance. And so these are disjoint key spaces, right? So nothing in here on the bottom can have the same key up here. And I'm going to continue to subdivide on the key space until I finally get to some point where I'm happy, and I'm going to reconfigure the hardware to now do hash mode, like naively, like as I said before. Okay? So this is a case where in hardware, we can configure at runtime this operator to do partitioning, and then suddenly we can switch over into hash mode. So there are many more details that I'm glossing over, but I'm just going to skip to kind of evaluation. These are just a set of kind of workloads. K-means over here. We measure some of the operators in isolation. The stuff that's y-axis and log scale, this is performance normalized to code that's running at C# on the ARM processors. Okay. So first thing to note is what's shown in blue is the application parallelized, ported over to C and parallelized across 2 threads. Okay. And you can see already actually that just by writing better software, we get pretty good efficiency. Right? So we have high-level programming language, but we're actually paying a lot in terms of runtime overhead, dynamic checking. This is LINQits. So LINQits is basically, we're now getting another order of magnitude on top of what we can achieve in tuned software running on the ARM cores. Okay? Now, speed up isn't the only thing that's important. As I talked about, energy, right? We care about energy. So first I'm going to show is power. Okay? So these are the same applications. I dropped the C# result, just the C and the LINQits. And what's highlighted in red is the amount of power that's spent computing. Okay, so this is the power of the cores, roughly around 600 milliwatts. What I'm also showing is the DRAM power consumption. Right? That's actually pretty substantial. In some cases, exceeds the power it takes to do compute. What I'm showing you here now is LINQits. So LINQits actually burns more power. Okay, so I went to an accelerator and actually increased the power. Okay, and I've also increased the power of the DRAM. And why is that? And the reason is because I'm actually going faster. I'm actually driving the memory system harder. I'm actually going at memory bandwidth level performance, so I've actually increased the power consumption. However, with that being said, because I'm going faster, my overall energy gain is still a win. Right? So across the board, I'm still getting significant gains in energy to actually complete the task. Now, one thing I want to say is that I'm only measuring the kernels. So I'm not including, if this is in the context of a larger application, these are just the raw kernel performance efficiency. Your mileage could vary. I want to make a little bit of a comment here. So we initially set out to do this work with the mindset that the Zinc was just a vehicle for prototyping. So we said, OK, we're going to actually turn this into an ASIC. It turns out that the FPGA gives us a lot of efficiency. And there's actually, within the architecture community, I think there's a sweeping generalization about FPGAs in that they're not efficient enough because it's all the fine-grained reconfigurability. And so this here is actually a computer architecture 21st century community white paper, and I kind of singled out a single statement that echoes that sweeping generalization. So my response to that is that there's a thing called Amdahls Law, and we all forget it. So going back to kind of these charts that I showed that kind of look like this, if I bring compute power to practically 0, right, I still have system level overheads. I have things like not just DRAM, I have the screen, I have the radio, right? So unless those things also improve commensurately, it's not clear that we should always just say, let's do an ASIC, okay? And I think ASICs are still relevant when, if area is constrained, so it's no secret that FPGAs consume a lot of area. If the FPGA still isn't able to get you memory-bound performance, the ASICs will still go faster. When you think 2x efficiency still matters at a system level, or when many applications will benefit from it. So how am I doing on time? 7 minutes left. OK, so there's a lot of interesting future work that we can envision with this. Presently, the user-defined functions, I said, we use existing tools. Currently, it's a semi-automatic fashion. We're trying to work towards automation. Of course, we think there's a lot of interesting deployment scenarios in data centers and clients. There's a lot of work to be done on kind of how data is managed, right? What are the data structures for managing data between the accelerator and software, and query planners that are actually hardware aware, and also support for rich data types. We think FPGAs actually are really good for supporting irregular data types, things like variable length strings, or if you have bit-level operations, it's very effective. And of course, we have a list of wants. Like we want some features that are missing on the FPGA and the Zinc chip is that there's no virtual memory for the FPGA. So you have to basically pre-allocate a bunch of physical pages and then work out of that scratch space. And that's pretty limiting. There are also other interesting declarative domain languages, regular expression, XML. And the question now is interesting, should we think about explicit language support for logic specialization? So far, I'm not willing to touch software, but maybe we should. This is just a one-slider on other work I've been doing at Microsoft Research. This is kind of a different context. It uses FPGAs, but this is FPGAs for specialization of the network in the data center. And we're being a little heretical because we're actually throwing out packet-based switching altogether in favor of circuit switch networking, which actually makes a lot of sense in the data center. And I'm happy to talk about that offline. So this is kind of my second to last slide, and this is really kind of my long-term agenda. Okay, it's a squishy agenda, but this is at this point in time what I think needs to be done. So what I really care about is enabling entirely new capabilities that wouldn't be possible if we were just doing the same old. Okay, this in both the data center and energy-constrained devices. So in terms of data centers, of course, we want to increase compute capacity by order of magnitude. In mobile devices, there are some capabilities that we can't do right now. So augmented reality all the time, speech recognition always on, personal assistance, and I think special purpose hardware can actually enable these capabilities reasonably within a 5-year time span. As I said, I don't just want to take the applications and map them. I want sustainable methodology at all levels of the stack in order to support this. So of course, as I mentioned, hardware runtimes, development tools, operating systems. I'm also really interested in this notion of patterns and whether we can mine these patterns semi-automatically or automatically. So I already gave you 2 examples of patterns. I'm also interested from the bottom up, okay? I talked a little bit about this domain-specific language for hardware. I also think this notion of declarative hardware design is feasible. So the idea of design patterns is actually a pretty well-known idea in software engineering and other fields. I think we can actually mine and catalog these design patterns in hardware and actually formalize them in the language. At the much lower levels of the abstraction, I'm also interested in debuggability. So FPGAs right now, it's actually getting worse. You have millions of gates, but you can only probe 1,000 signals. And you can only watch them for like 1,000 clock cycles. I think there are a lot of interesting ideas in computer architecture related to checkpoint, rollback recovery that you can actually apply. So I have some ideas about how you can re-architect the slice to not only be a logic gate, but also to be able to checkpoint state. So I also don't think we can sort of address these issues just from software alone. From research alone. I think that it's also a pedagogical issue. So we need to train people to understand how to exploit special purpose hardware. And this would involve things like curriculum, innovations in the curriculum, and also doing a lot of workshops and tutorials and bring awareness to this area. So in conclusion, I think that logic specialization has a disruptive potential. There are a lot of grand challenges that lie ahead. In many ways, I think the hardware is kind of easier than the software, right? So programmability, portability, debugging, graceful integration with software ecosystems. So I presented 2 projects today, CoRAM and LINQits. These are abstractions at different levels of the stack, and I think it's a first step towards logic specialization for the masses. So with that in mind, I'll stop here and take questions.
Does dark silicon affect your future roadmap on FPGAs as well? Like, does that
That's a good question. So the question was, does dark silicon affect the roadmap for FPGAs? The interesting thing about FPGAs, they're not even near hitting the thermal limits. So if you take the biggest FPGA today, it's about 50 watts. So it's interesting. The question is, in an era of dark silicon, would I rather just have use my area to have hundreds of little ASICs, or I can have one big monolithic fabric that I can dedicate to the accelerator? So I have a feeling that the answer is something in the middle. Yeah.
All right, thank you.
All right, thank you.